line that closes. If it's a relay, that means that it's not manually flipped. We use what? With the relay, it's going to have some type of coil in it, right? So it's a simple, normally open or normally closed switch. So if you have a relay, it'll have a normally open or it will be normally closed. This is an either or. Because single pole simply means you have one line that you're breaking. So these are two separate pictures. This is showing you a normally open, and this is showing you what a normally closed symbol is going to look like. These will have a coil associated with them, usually 24 volts on our system. Some other systems, when you get into commercial or in any type of bigger refrigeration, is always usually line voltage, so 120 or 240. Oftentimes you'll see a coil symbolized with some type of circle. There are several different ways of showing coils. If I look at this one, can anyone tell me what 2 points my coil is in between?
3 and 1.
He says 3 and 1. How did he know that?
Sure. Because of the thing that coils around the cylinder.
That's right. Because you can see this symbol is representing a coil of wires, right? Going around that pole. So that will be my coil. When it's energized, it's going to pull in and move this switch. These diagrams are always shown with the coil de-energized. So that's what we call the normal position. That's a test question. Normal refers to when a coil is de-energized. Remember, just like our contactors, that is a separate circuit altogether from whatever these switches are doing. What is my coil voltage on this system equal? 24 volt coil. If I put 24 volts on this, I'm going to activate it or energize it. This is what it looks like when it's not energized. I have a normally closed set of switches between which 2 points? Don't say it out loud yet, just think about it.
You said normally closed?
Yes, in this picture, there's a set of normally closed switches between two of the terminals. If you can look at it and tell me. Matter of fact, we can do our hands on our chest, so just throw it up. Which two terminals by number do you think are normally closed? All right, don't look at JAWS. JAWS is a different kind of relay. Do it on this one that we have up here on the board.
I need to move my foot.
Yeah. And I'm going to erase this. Y'all remember what type of switch I said this was? It's not a single pole, single throw switch. This is actually a single pole, double throw. That's another way of drawing the same thing that manufacturer has on the sticker. All this means is I have one terminal right here, and it's power, if I send power in right here, it can come out on this one, or it can come out on that one, depending on whether the switch is energized or not.
What was the two that was normally closed?
I haven't told you yet.
Oh, okay, so.
All right, can you tell based off of that drawing? All right, so which two?
4 and 5.
Good job, 4 and 5. Now what they're showing you, 4 is connected with 5. You see that little arrow on it? That means there's a connection there. If you look close, there's a gap between 2. So what will happen when this thing is energized is it's going to pull that bar over and make a connection between 4 and 2. See, 4 is always connected. I said 4 is always connected. When it's energized, it will pull 4 over to 2. So imagine that's just like a lever that's going to be controlled by the coil. So it's either touching 5 or it's going to be touching 2. 2 will never be touching 5. The only thing we're doing in this picture is swapping 4 from being connected to 5 and making it connected to 2.
So 5 is open.
Do I? Yes.
Energized.
Right, exactly right. If this coil gets energized, 5 would open and 2 would close.
So where would the electricity be going if it was closed on the 4 and 5?
All right, let's flip it over and look at it. The short answer is, if I've got it going in on 4, electricity will be coming out on 5. Just like a light switch, it's flipped on. So when I energize that coil, I'd have it coming in on 4 and then swap to 2. Does that make sense?
Mm-hmm.
And let's say, for instance, we had this going to 2 different fan speeds. It would not always stay on fan speed, whatever I have hooked to 5, but if I energize that coil, I'd swap it over to 2.
Kind of like going from high to low.
Right. That's the way to go from high to low, but if we do that, we're gonna have to add something else to it, or else 5 will be energized all the time, right? So there has to be some other type of switch in there. But we do that, and that's kind of what we're working towards. If I flip this over, you can see these are labeled. They're labeled kind of funny, so you have to pay attention to what you're hooking it up to. Remember, y'all's is a little different. So we're going to go over several different kinds of relays. So looking at this one again, what is my coil between which 2 terminals did I put 24 volts on? 1 and 3. So if I'm looking at this, do I see a 1 and a 3 anywhere?
Yes.
That's 3, right? It's hard to see from this, but that is 1. See how that's 1 and that's 4? Can y'all see that? So my 24 volts would need to go on that terminal and that terminal. Right? I'd send common to one of those and then 24 volt hot to the other. It doesn't matter which. But just like my drawing, my 4 is normally closed to which one? That or that?
5.
All right. So which one is 5? This one?
You're right.
All right. That one?
Yes.
That's right. So this thing's sitting like this. Whenever it's energized, all it's gonna do is shift to here, that switch here. De-energized, energized. Does that make sense? There's really not a lot to it. That's a single pole double throw, because we're only breaking that one side of power, but we have two options on where we need to send it. The pole refers to how many sides of power we're breaking, and throw refers to how many directions we can send it. Does that make sense?
So, I would just define normally closed.
Normally closed is when is a closed switch when power is not applied to the coil.
And normally, that's normally closed.
Yes, it's a closed switch. Normally means when power is not applied to the coil. So if that coil is not energized, you're in your normal position.
And, normally open is normally closed.
Yes, if the coil is de-energized, those 2 points are open.
That was my problem on that, you know that one test that was like earlier, probably 4th or 3rd week? We had that test online, and it was like all the questions about the relays, and I had no idea, like, if it was supposed to be energized, or not energized.
Oh, if it was energized, I'm normally open, normally
Yeah.
closed and all that, yeah. So this is not new to you then, right? You've already read all that in the book.
Oh, yeah, I've totally read it.
Alright, I thought so. So what's my set of normally open switches in this relay? Don't say it out loud, just do it on our chest. Between which relays are normally open? Or, sorry, between which two terminals are normally open? Alright, which two? A lot of people are just putting one up. There's gonna be two terminals. I see a lot of different answers. We got all kinds of variety out here. Alright, my normally open switches or contacts are in between 4 and 2. These have nothing to do with it. That's the coil,
Okay, that's the closed.
right? So we're only talking about these 3. 5 and 2 will never touch each other, so they're not even really a factor when we're talking about normally open and normally closed, right? Because it don't matter if we energize it, they're never gonna touch. Normally closed is 4 and 5. Once it's energized, my normally closed circuit will open, and my normally open circuit, which is between 4 and 2, will close. Now, that was single pole, single throw. I'm sorry.
Double pole, double throw.
Single pole, double throw.
Someone had been reading the book.
Do what?
Define that single pole, double throw.
Alright, one line in, 2 lines out. And the 2 lines out are an either or situation. I can either send it out on one line or the other line. This is a double pole, double throw. All it is 2 single pole, single throw switches built into one. That's the one you guys have right here. I'm gonna give y'all a chance to look at these on your own and see if you can tell me what my normally open contacts are and my normally closed contacts. And see if you can find where I would hook my coil voltage up to. Cause that looks like a whole lot of terminals, doesn't it? So I bet if you take some time and look at it, it'll simplify pretty easily. And this is just like the one you guys have. And bear in mind, these cannot handle the amp draw that a contactor can. So that's why you can't substitute a contactor for one of these. And look at that, what does it say? It's amp draw. 8 full load amps at 250 volts. 18 lock rotor amps is the max this can handle. Made in China.
Oh, my made in Mexico.
Oh, yours is made in Mexico? Yours have a brown one. Know where this was made. This one can handle 82.8 lock rotor amps and 13.8 full load amps at 120 volts. What's my full load amperage at 240 volts?
41.
What is my full load amperage
6.9,
at 240 volts?
6.9.
Can this thing handle 277 volts?
Yes.
What's its maximum full load amperage at 277?
15.
15 amps.
Well, really, it's 6.
6.
If it's full load amps.
What's the 15?
That's its RES.
Okay.
I don't know, I'd have to Google that and see what it means. I'm sure it says in the book.
Probably something resistant.
That's why I was wondering if it maybe means resistive load, maybe it could pull 15 amps, probably because maybe it's saying, we got 36 locked rotor amps, which means it's a motor. Locked rotor amps is that instant that a motor starts. It takes that half a second for it to start turning, right?
Yeah.
And while it's not turning, it's pulling a tremendous amount of amperage. So 36 locked rotor amps, but 6 full load amps. Maybe it can handle 15 amps of a resistive load.
Mine also has a half horsepower.
Does it?
Yeah.
The reason I don't know that is because I don't use this for a resistive load. I don't use this for a compressor. The only thing I would use these for is a fan motor. And no fan motors that I have are gonna be pulling more than these amp draws right there.
Okay.
That makes sense?
Yeah.
So if I were gonna use these in other applications, then you absolutely wanna check all these specs on it and know what you're using it for, make sure that it can handle that.
like a,
But for us, it's really pretty simple because we only use them in limited circumstances. All right, did y'all have a chance to look at these? All right, who wants me to call on? Who wants me to pick on? Raise your hand. All right, let's stick with Greg. Tell me one set of normally closed switches.
1, 2,
All right, he says between 1 and 2. That's correct. Gavin, can you tell me another set of normally closed switches? 4 and 5. Awesome. Steven, can you give me a set of normally open switches?
4, 2, and 3.
Huh?
4 and 6.
Yeah, 4 and 6. And on the top side, what do you think, Nick? What will be my open switches on the top side? Not 2 and 4. This, the one you have in your hand should be labeled the same. What you think, Christian?
1 and 3.
1 and 3 is my normally open switches. 1 and 2 is my normally closed. The same here. So that's normally open, that is normally closed. So with this thing de-energized, y'all have your meters with you? Let's do a continuity check while we're here. Let's check on between 1 and 2 and 1 and 3.
I gotta go get mine.
All right. By the way, where's my coil terminals at? What would I hook my 24 volts to?
Bottom.
The bottom one. Notice there's 4 of them right there, correct? These 2 are the same thing. It's just like on our capacitors where we have, just 2 spades connected together. So that's one side of the coil, and that's the other side of the coil.
And then you just run off the other two?
Like I could put common right here and 24 volt right here. Or I could put common here and 24 volt there, or there. So I could swap them. Common here, 24 there, but I'd never put them both on one side. That's a direct short. Got that? Good with that? You're looking hard on that. You think I'm lying? Let's try it and see.
What if I got one about to fall out? Old raggy.
Broken one?
It's reading, but it's
Yeah, give me
still
that on the crack one.
jiggling.
I got a brand new one that's that way too. Oh, yeah, that's garbage right there. There's one for Debbie right here.
Give me that one.
Cheap piece of garbage.
Well, what should I do?
I said this on wood.
I don't know, you tell me. What do we set it on? Relay that, man.
Just have to own
Which ones are really closed? 1 and 4, right?
Alright, so we set our meters to ohms and we check continuity. Go ahead.
Between 1 and 2 and 2 and 3.
Even though I need it close.
Yeah, 1 and 2, 1 and 3, then 4 and 5, and 4 and 6. And tell them to check y'all go ahead and check the coil's resistance too.
24, 21.
Which one was 2, normally closed or normally open?
2?
2, 1's closed.
Yeah.
Is that correct?
Yes.
And check my coil, resistance as well.
Where is the coil?
Bring up a good question.
Oh.
So, if one is full,
You will try it out.
So if these two are connected together, that's one side of it, this is the other side of the coil. You need a terminal.
so if it's a closed switch, should you be getting resistance?
So we can check if they're or not.
Yeah.
Should get something.
What's that now? If it's a closed switch, you should have almost zero resistance, which means closed. That electricity can flow with almost no resistance at all, right? An open switch would be the same thing as holding it up in the air. You should get infinite resistance, or OL. There's a difference between 0 and OL. 0 means it's a closed switch and there's no resistance. OL, or infinity, means it's open and there's no path for electricity to flow. Be careful if you're holding it with your fingers, because you'll read the resistance of your fingers through your body. Or even, if you're checking the coil, it's fine, but if you lay it down like that and it's touching the table, that'll be a path of electricity to flow. So every time we're ohming things out, we have to make sure it's completely isolated.
So the only thing we should be getting resistance for is the coil, right?
No,
No.
1, 2.
We're supposed to be getting.
When you say resistance, you mean 0 or 0.1 is a resistance value. That means that switch is closed. There's almost no resistance there, but that's different than OL.
And when it's open, you don't have OL.
Correct.
So,
I was on out fan motors once, and when you check motors and things, you check from the windings to the case of the motor. Check the ground to see if it's grounded out. See if there's a short inside of it. Well, I checked to the ground, holding, and the wires inside, and I got a reading. So I thought it was a bad fan motor. But what I realized happened was, if I picked it up off the ground and I set it on a table, I didn't get that reading anymore. I was actually reading the path to the ground itself through me, from standing on the ground, through my shoes, and then through the motor, sitting on the ground.
Why would you do that?
Because we're all conductors. We have a good bit of resistance, but if you grab two hot wires, electricity will flow through you. So, matter of fact, hold your leads in your hand, let's see what your resistance is. You gotta hold the metal part. What's your resistance?
1.7.
Is that kilo ohms or mega ohms? Mega ohms. That's a lot of resistance. But it's still a path, right? The electricity will still flow through it.
so,
So OL, when it's old, when the meter is reading OL, that means it's open. When it's zero, it's closed.
Right. See what you're saying.
Dude, you're freaking losing.
OL, that's 1 and 3.
You all good day, mate.
Or something, yeah, that's a closed switch.
And diagram shows you that, when these.
Hey, now.
Open.
I've already got a pee, I need my bladder.
So that's normally open,
Mhm.
and that's normally closed. If you wanna swap their positions, you energize that coil. So when you put power on that coil, we would swap between being closed from here to here, being closed from here to here.
Interesting.
Does that make sense? My normally open line will close, my normally closed line will open.
Wait, so is 1 and 4 not a closed?
No,
Then why is it connected with no
it's not.
switch?
You connect between 1 and 4, you should not get any continuity.
I'm not, but why
Yeah,
is
so
it?
that's crossing, that's on the other side.
Yeah, they're not even related to each other. One doesn't care anything about 4. You can
Wait.
have a high voltage on 1 and 24 volts on 4, if that's what you're trying to make or break.
Or you can put your meter on sound. Got continuity.
I'm trying to figure out why, okay, it's on the top one right there, it says 1, it looks like the 2.
Alright, be specific. Say 1 and 2, so look up here with me, make sure we're talking about the same thing. So 1, right there, right?
Yeah,
And 2 right there.
yeah, so
That
is that
should
a
be closed.
switch on that diagram?
That is showing a normally closed switch. See how that's a normally open
I
switch?
thought that was a 4. It looked
And I
like just
think
like a
is that what
4.
you thought too, Nick?
I was looking at one of these.
Oh, okay.
Yeah, I thought that was a 4, it looked just like one.
Yeah, that's not a 4, that's the same symbol that I've got drawn on the board for a closed switch.
That makes sense, I was a little confused. See the bubble ice cream,
The numbers are
I
crazy.
know it's real. Hey, you must really like football on that. Listen, you must really like football. College or NFL, football. NFL freaking. I don't know themselves.
That's a solid connection. It's a whole connection, yeah. No, it doesn't have to the top of bottom. Just make sure you got good pressure against it so it's a good solid connection.
I care about.
No, that's why I did the top and the bottom, so I could push against it.
No, I'm just.
So I did the top and the bottom, just so I could push against it without sliding across the table.
Is it?
Yeah, you can use the pinky to,
Oh, that's more can you do. That's back when you were like 10 yards.
yeah,
from
just
the
to keep it
church.
flat so you
It's
get.
ridiculous, we're like overpowered.
I thought that was wrong there.
No, you good? And just as a side note, your meters will read the least resistance. So if you were to hold the meter leads in your hands and put them on 1 and 2, you would get almost no resistance. But if you were to hold them in your hands and hit that open line, you still read your body's resistance. Does that make sense?
Question,
Yes.
on the, what a coil is connected,
Uh-huh.
on the very bottom.
Yeah.
When you read 1 and 4,
Well, they're not labeled.
we're not labeled, right? The very top one on the left and the bottom on the right. And the very
You
bottom.
talking about this one?
Yes, sir.
So if I'm looking at my coil and I do there to there, I should get the same thing if I were to do there to there. But you got yours laying on the table. Oh, you can be reading it through whatever it's sitting on. It has to be completely isolated.
Can't be in my way.
As long as the terminals aren't touching anything, you can. But don't let them lean against your shirt or anything. Oh,
It's not like you checker.
they're reading down in the milli IQs.
Yeah.
I'm just says on.
18
Just stab or something.
What'd y'all get in the resistance of this coil?
21 truck.
Right around 20 ohms of resistance?
Yes.
Cool. So now you know, if you go up to one and you get about 4 ohms, it's probably a problem with it, right? Does this relay make sense to you guys? Could you use it? How about you, Gavin? Do you use this relay? Would you use this relay to bring on a light bulb?
So say hypothetically I stab somebody with these leads, would it kill them?
Yes, depends on where you stab them.
Oh, yeah, that's what you're saying.
Try to like Ben Shapiro.
Somebody needs cancer.
Alright, those are relays. Single pole, single throw, double pole, double throw. What about a double pole, single throw? Do I? Sequencer? Possibly. It would be a double pole, double throw.
There's a
Double pole, single throw.
Especially when it's up the road. Great.
Does that look like anything we've used so far? What?
Contact.
What about a contact is a good example of a double pole, single throw. We have 2 legs of power coming in, but it's only gonna go out. Each leg will only go out in one place. It doesn't have an option of sending it somewhere else. So it's either open or it's closed. Good? Good.
It's like your light switch,
Able to keep up with that?
like your light switch.
A light switch would be a single pole, single throw switch. This would be double because I've got 2 sides of power coming in,
Okay.
or at least 2 inlets. But each inlet only has 1 outlet.
I thought you were saying.
You good with that? All right. Is that how you spell cylinder?
Sure.
I think you got an E.
Do what?
That we're spelling it today.
Solenoid. A solenoid is not spelled like it sounds.
Something paper tag.
I'm pretty sure that's right. I didn't go for spelling, I went to school for it.
Same here.
It does have an E in it.
Oh, really?
So close, 1 letter away.
I messed up.
Still stupid.
So
Use it in a sentence.
The solenoid is what energizes my relay. So when I create my little magnetic field using my coil of wire, gentlemen, I've created a solenoid. Anybody ever heard the term solenoid used in automotive?
Yes.
What is it?
Cylinder.
Not a cylinder.
On your starter.
On your starter, it's called a starter solenoid.
Yeah, solenoid switch.
Because when you turn your switch, all you're doing is completing a circuit to that coil inside your starter, which closes the power supply to it and energizes your starter. That solenoid is what we're talking about. And we see that symbol like we had on the relay. When we create that magnetic field and we pull that little bar down to open and close switches, that's the solenoid. That's all we're talking about. I've been calling it a coil. Really, a solenoid is another word of saying the same thing. But a solenoid doesn't necessarily have to just close switches. It can actually, go ahead.
Open switches.
It can open switches as well, but it's not even just for switches though. We use this in our liquid line solenoid to block off the flow of refrigerant. You can put it in a water line. You have water solenoids.
Put in a purifier.
In a purifier. And it'll actually, instead of just energizing switches, it'll have a little plunger on it that can open and close. That's your water pipe. You energize it, you can close it off or open it up to allow or block water from flowing. But it's just a coil that moves that cylinder inside of it, or whatever it is you're using. So you could actually use a light switch to turn a water faucet on and off. I've always thought that'd be pretty funny, right? Tell somebody to turn your water on, they flip a switch, start spraying out of your hose. Then you can use a little gate valve to turn your lights on and off. You can really mess with people. So the reason I talk about solenoid is because that's what energizes these relays and my contactors. Let's look at another component. Before I look at that, I forgot. Let's look at your relay that you have. And let's see how it's different from the first one I talked about up here. Then we'll move on to see.
Solenoid is not the underlying component.
Yeah, solenoid is the coil of the relay, or whatever you're using. So the solenoid is what's actually creating the electromagnetic field, moving the plunger or the switch. Do what?
Put a solenoid valve in for water pipe to flip the switch.
Yeah. Keep saying it for years now, I've just never done it.
We just been doing it wrong all this time.
That's right. There's too much manual labor opening and closing it.
Yeah.
Right? The reason I hadn't done it is because a solenoid valve for a water line is like $75 or more.
There's that.
It's a lot cheaper to buy.
Well, you think you're paying that much for a hose anyway, so
Do what?
might as well.
Yeah,
They're expensive.
yeah. But I still want to make one for my dog's watering bowl. But I don't have the water. So I have a float switch or something in there, when the level gets low, it'll open the solenoid and fill it up. Then when the float switch gets high enough, it'll shut the water off. Then I don't have to water my dog anymore.
Like a toilet.
Pretty much like a toilet.
Or you can put a switch up there so it's.
Yeah, or if your dog's
Do it
smart
with
enough
water
to
for
train.
dog.
My dog just mess with me and run my power bill up. He probably go to sleep on it. Full of water out everywhere. All right, looking at the drawing, can you guys tell me, they look a little bit different, but I want y'all to see it and think about it. If you're in the field and you ran across this, would you be able to tell what this relay's doing versus that relay? Don't say it if you know it, just look at it and see if you can figure it out. The one thing I hope y'all learned is that all these symbols don't look the same, right? Many manufacturers have their own way of symbolizing this stuff. I wish I could give y'all a handout of, hey, these are all the symbols and they'll always look like this, but they don't.
Is it the same company though?
Yes,
They decided to switch it up on us?
yeah, they flipped the script on
On your trailer, like, you take it apart.
it. Do what?
On your trailer, like, you take yours apart.
No. You take yours apart?
Yeah, you can see it.
Oh, yeah, you can pop those little clips off on the side. You already got yours apart? Yeah, let's see. Don't everybody do that, because y'all gonna break them, and I'm gonna have to buy all brand new ones. But no, that's cool, my,
Well,
for
for
sure.
sure.
You can throw it into the brick wall,
Yeah, that's pretty cool. This kind right here, you can actually pop apart.
Better when you see it first, you know what I mean?
Been up here on the screen, or you just mean with the
Like
cover
that.
off? Yeah.
It's basically cheap. Yeah.
Now you can, you can
I mean,
change out the
focus,
internal
baby,
parts.
focus. You could, but for the cost of these, I wouldn't.
True.
Come on, man. Where's my focus button?
Why does that plastic go in the
It looks like you can't use it. It's back for the bag, so it's not trying to. There we go. It's real easy to tell what y'all's is doing now. There's a spring holding that and that together. So these two points are connected, right?
Those are normally closed.
That's normally a closed set of switches. Once this thing creates an electromagnet, it's gonna pull it this way. What happened to these two sets that were normally closed?
Open.
What happened to these two that were normally open?
Close.
Oh, okay.
That right there makes a lot of sense as opposed to the drawing. See what it is.
See what it's doing? Let's flip it over and look at the drawing now. What's my coil between? What's my normally closed set of switches? See how it's 5 and 6? Between those two terminals, there's a bar showing they're normally connected. What about between 2 and 4? What is it?
open.
It's normally open. See, the bar that would close those is not connected. You get this thing off, man. Use your, what? How'd you get this off?
Good thing.
He gets a cover.
So we do it.
You have to use it, help that.
How do you explain it to tell you that it's a one-way operation?
Do what?
You said the market declined to tell you that it's a one-way operation.
Yeah, exactly.
That's what I
All right, we look at this again. What two terminals are these?
That would be,
Two and four,
That's fine.
That's cool. Let's count.
Look at this thing operate. That's my normal position right there. If it's energized, it's gonna pull us that way. In my normal position, are those two open or closed to each other? They're not open to each other. That's a closed circuit. By the way, closed means there's a path of electricity to flow. If I switch that on, it's closed, yeah.
Oh, if you look on the other side, you see a little, like a little tab that will connect with the pool when you push the switch over.
Stop lying.
See a little makes contact with the pool.
You been drawing on it, dude? What are you doing?
What are you talking about?
I think he's on something. He him out the flash.
See that? So, yeah, that makes contact with the pool.
These are unite. Yeah, flathead screwdriver, they're not. What is that, a spatula?
Wait for my job at McDonald's after class.
That's what you use for beer, switch my hands, well, like the business.
Whoa.
Alright. What he was saying is, once this coil gets energized, I'd imagine that becomes the magnetic part, right? And then it's gonna pull that up. When it pulls that up, that lever pulls that down and close the other set of switches. So my normally closed set of terminals are here and here, right? What numbers are they?
Which one's the bottom?
It doesn't matter whether top or bottom, what I'm saying is, this set is normally closed.
That's one.
2 and 4.
2 and 4 is normally closed,
What's up, Bob?
they look like they're open. Look at 5 and 6, see how that bar's connecting 5 and 6?
Yeah.
They're the normally closed to have contact. And if I energize this, which 2 sets of contacts will close? If I energize it. 2 and 4. So that means these are what? Are these 5 and 6 or 2 and 4? They gotta be 5 and 6 because they're closed. If I trace it around, let's see where it goes. That goes over to here, mounts to there, which is 5. So that I would expect to go to the other side of my normally closed switch, which it does.
What a shock.
Had a game war back here.
Yeah, so I'm thing you think of, that,
So what's the difference in these relays then? Y'all see any difference?
I don't know, I can tell you that one.
Diagram's different, is their operation the same or is it different?
But it does the same thing, though.
Same concept.
One don't have 6 on it.
Might have a
One or so.
This one is a single pole double throw. It can send 4 out 2 different places, right? This is a single pole, single throw, and a single pole, single throw. We have 2 single pole, single throw switches right here, right? On their box, they call this single pole. What's that mean?
Normally open,
And then single pole.
normally closed.
So that's their description of what you're getting when you get this relay. What you guys are gonna do, you're going to turn this into that. Oh, you know.
That one is the
Ain't
single
no
pole.
thing but a chicken wing.
That one is the, single pole. No, the first one is the single pole, double pole.
Yep.
And
This one they're calling single pole normally open and single pole normally closed. So, how then do I turn this into that?
How do you turn what into what?
No, I would have to, run a pole,
Don't use the water, don't be careful.
pretty much what that looks like, right?
Pretty much.
But what I wanna do is come in with one line of power, right? But be able to send it out either way. So in other words, I want one inlet and two different outlets. So look at that for a minute and think about any way you could use that relay to do that job.
So you need to hold it. Oh, you need to hold it. What is this? Let's go. I don't know if this will help you out any or not. But this is the same relay. Only one is being used like this, and the other is being used like that.
Are you saying that's one layer, that's two layers?
Well, it's two different relays, but they're made the same, but if you look at them, one is being used like the bottom picture, and the other is being used like the top picture. So look at that for a minute and see what differences you see in the physical characteristics of those two, and see if you can think about why it would look that way. It's kind of a vague hint. Maybe it'll get you thinking in the right direction. Can y'all see these relays very well? Yes. So first step is to spot the difference in the two. Second step is to think about why it's different and what you could do to simulate that.
I see the blood of the technician.
I got it.
Do what?
I see the blood of a technician.
Yeah, somebody probably led doing that.
Six on. They all right?
Do what?
Just break six off those relay.
Break the 6 off? You got a good start on it. Why do you think this one doesn't have a 6 on it? So he said the first thing to notice that's different, the 6 is missing on this one.
It ain't like another one, like 5 and 2, normally closed.
So y'all keep thinking about that for a minute. What did they do? They took the 6 off. Why? You know you're gonna put 24 volts off that. Remember, my coil is completely separate than my switches. I can use my 24 volt coil to control 120 or 240 volt switches or 24 volts on the switches. It doesn't matter. The switches don't care as long as it's within their rating. But the coil has nothing to do with the switches. Does that make sense? The coil could be 24 volts, it could be 240 volt coil. But it still has nothing to do with what we're switching up there.
Okay.
Oh.
I'm running to get that younger skin. Can you throw it?
It's just, not what they're putting here. It's like Lego's times 10. Like Lego's times 10. Hope you guys take a shot. We're just negotiating.
Negotiating.
Yeah, I think good. Don't tell anyone what you're ready.
All right. Here's your next clue. I could also use, or I would need to use one of these. Jumper wires to do it.
Are we saying this out loud?
Do what?
Are we saying this out loud? or
Not yet. Obviously, I could just tell you guys, right? But the important thing about this stuff is that you understand how it works, and you understand how to adapt when you're in the field. Yesterday morning, I got here before they unlocked the building, so I had to kill some time. I went over to Donnie Dunn, a block or so over, to talk to him for a while. And he was telling me how one of his techs that finished school, was just starting out there, basic electricity, so they had a heat strip. They had a board that brings on the heat strip and also brings on the fan when the heat strip comes on. The board was bad and obsolete. So Donnie asked him, well, what should we do? Sell the new unit. Said, well, you could, or you could use a sequencer and a fan relay to do the exact same thing. Which is funny because that's literally what I have printed off for you guys yesterday, is how manufacturers use a sequencer and fan relay to do that same thing. So when I go through all this stuff, all these different ways, it's because when you get in the field, you need to be critically thinking and understanding this stuff, knowing how they're used and how you can use them. So what do we think? That's about all the clues I can give you. Who wants to volunteer? All right, Kyle?
The 6 terminal and the 4 terminal in this case are internally bonded.
All right. He said, in this case, the 4 and the 6 are internally connected. So in other words, we could take a jumper wire between 4 and 6 on ours. And let's think about how we're doing the same thing. Let's say we have power coming in to 4, right? I'll just call it L1. If L1 is on 4, L1 is also on 6. Which gives me a normally closed connection between 4 or L1 and 5. But then what happens when my coil gets energized?
It makes both lines closed. 2, 4, 5, 6.
I still have L1 on 4, and I still have L1 on 6, right? But once this is energized, and I'll symbolize that with a little lightning bolt, it's gonna pull my plunger up and close between 2 and 4, but open 5 and 6. When I'm energized, that opens, and now that's closed.
But wouldn't 5 and 6 still have, electricity in it?
No, 6 would have it sitting there, but it's not going anywhere. Because I pulled it that switch open between 5 and 6. So all I've really done, I sent L1 out on 5 here, but then once I energized it, I sent L1 out on 2. So I actually turned this into a single pole double throw simply by connecting 4 and 6. Let me see that again.
Okay, so you're just bypassing your coil altogether.
We're still using our coil to make and break connections between 2 and 4 or 5 and 4.
So 6 is providing power to the coil.
My coil will be down here. It has a completely separate power supply.
Okay.
Whatever I'm putting on 4, I'm just jumping and keeping it on 6 all the time. So essentially, like he said, I've just bonded 4 and 6 together permanently. And so instead of having 4 and 6, I would just have,
Okay, I see.
this scenario, this one got a stupid diagram. I would really just have a similar scenario here, where I've got 4 either going to 5 or going to 2.
Okay.
Because 4 and 6 is the same thing, right?
Yeah.
Is that a little tricky?
No, you basically,
So basically 4 and 6 is becoming your,
4. Yes, when I jump 4 and 6 together, now I simply just have 4, and it's connected all the time to 5, unless I energize it, in which case it connects to 2. So if I've got 4 and 6 right here,
is your close.
yeah,
Close.
and back up, so you can see that. So this is normal position, right? So you can see between 4 and 5 is normally closed. Between 4 and 2 is normally open, right? Once I energize it, between 4 and 5 is now open. 4 and 2 is now closed. Need to look at that a little bit?
Yeah.
Look at it, let's think about it. What's a better way of explaining that? Anybody know? Does that make sense to you, Carson?
So you're repelling the coil.
Nothing to do with the coil. Coil's still just a coil, still
So
doing what
you
the coil
don't
always
energize
does.
the coil.
The only thing I've done is I've put 4 and 6 together, so that I can eliminate 6. I can pretend 6 don't even exist.
Okay.
That's all I've done. So now 4, it's still sitting down here to 5 on a normally closed circuit. The only difference is, instead of that being internal, I had to make that connection outside.
Okay.
That
So you
makes sense?
still are, you're still powering the coil.
Yeah, the coil would still get its power whenever it needs it from a secondary source.
That's where I think.
Yeah, I'm not eliminating the coil at all.
Okay, that's where
I'm
I think-
just, yeah, I'm not bypassing the coil. All I'm doing is putting 4 down here where it'll have a connection to 5. I'm just doing it externally instead of internally right here.
Okay, now it makes more sense.
And I didn't intend to do this, but actually I thought I ordered that relay. But when it came in, I realized I didn't. I ordered this relay. So I said, well, I guess we'll have to turn it into the other kind of relay. Which is a good exercise in and of itself. Yes, Jesse.
So, if we were to wire this up, like how you got it on the diagram, you would just splice one wire, instead of having 2 different sets of wire to power both sides, you would just splice one wire, like on the L1.
This is what you're gonna get.
Oh,
Yeah.
that's good.
This is what we're
Stick it
gonna
over
make.
it.
This may not be long enough. I just snipped something off. We'll see. Y'all are gonna snip these off. You're gonna make a little jumper wire out of it, a permanent jumper wire. We're gonna crimp it to it. We're gonna connect our 4 and our 6 with it. But I'm also gonna need this. Little gem. Because I'm gonna need somewhere to plug my external wire on. I put what's called a little piggyback terminal there, so that I can plug 2 spades onto the same terminal.
That was mine.
Can you just use 5?
Did you use 5?
If it was closed, if it closed between 5 and 6, if you energize it, it closed between 5 and 6, then you just use 5.
Well, so you say if I jump straight from here to there, is that what you're saying?
Yeah, after you energize it and it closes that between 5 and 6, couldn't you just use the 5 tab?
Well, I
Instead of
wouldn't get the
having
same effect though. Because I've gotta be able to break power coming out of 5 and make power to 2 when it's energized.
Okay.
Does that make sense?
So with the,
But if I put just jumpers on here, now I have nowhere to put my incoming power wire, right?
Places you take the bar, you just split it like that.
Probably.
and then 4 is for the.
I mean, that's basically what you're doing.
Yeah, right. Instead, you mean instead
Instead
of
of
doing
going straight
this,
up down, you make
right,
it
you're
goes
just
angle.
going this, right, yeah, I know what you're saying. Go ahead, Derek.
The envelope, that's, yeah, that's the little.
That guy. And it don't matter if you put them here or there.
That's what you want the power.
Exactly. Whatever it is I'm trying to send power out to, will come in here and go out there when it's normally. Then whenever it is energized, it will go out there. So essentially, all I'm doing now is just switching between this half and there. So I'm just going normally here, switching to there. Normally here, switching to there. All I've done is bonded those 2 together so that they're one side of power. Yeah.
You could actually transfer that to the other side too, it would run functionally the same way.
Talking about if I put this over there? Yeah, but there's no real need to though.
But you would also want to make sure whatever you bonded with that with, like in this case, you're using the same wire that we're using, which is fine, but we wanna make sure if you're doing this in the field that the whatever bonding, however
Yeah,
you're
I mean-
bonding it is rated for
Yeah,
at
this
least
thing
what
can
the
only
relay is.
handle, what, 8 full loads at
Yeah.
250?
Here is
8
trivial.
amps, so even a 14 gauge wire can handle that much. It's probably weaker internally than it is there. But that's a good point, because when I first started teaching, I just had guys pull wires out of my, spare wire bin, just the trash bin, right? But then I realized I had guys pull a little bitty thermostat wire out there, and then they had big 8 gauge wire and everything mixed match, and I said, no, you probably better back up and do this right, you know? Teach them about it later. The little thermostat wire, he's right, would not be sufficient to carry that amperage. But does it make sense what we're doing? Cause that's what y'all are gonna have to do out there when we start doing the rest of those handouts I gave you. First thing we gotta do is make sure the jumper system easy. Those are relays. Are we comfortable with the relays? Feel good about them? How you doing, Stephen? Okay?
Okay.
Carson? Good. Christian? Gavin? About 3/4 of the way okay? Alright. Well, good. Let's talk about something else then, thoroughly confusing. That bad boy. He's a sequencer. He don't even give us no wiring diagram, does he? He said, if you don't know what I am, you better not be touching me. 'Cause I'm not gonna tell you. Sequencers are used to bring on heat strips. Put that in your notes. There's other ways of bringing them on, but the purpose of a sequencer is to bring on a heat strip. Electric heat, which means they can carry high amperage. The reason I'm going over all of this today is because when we get out there in the lab, I want to be able to stay out there for a little while and work on different projects using all of this stuff. And of course, I'll be around to answer questions about it for whatever you forget, but make sure you got notes. There's what your sequences look like. So let's hit the high notes of a sequencer. What time do you guys have? 11:40. Y'all need a break? It's a good time to take a brief break. Let's do 10 minutes.
That box okay out there?
No promises. Alright, we have a sequencer to bring on our first stage heat and our fan at the same time. A double stack sequencer like you guys will also, after a short delay, bring on our second stage of heat. It uses a small heater and bimetal disc to close switches. It has no solenoid. We're not dealing with electromagnetism here. When I say it has a small heater, I mean, it just has a really, really small one in your 24-volt circuit. It will wire up just like a relay. You're gonna put 24 volts down on the bottom, and then it's gonna close switches. But instead of using electromagnetism and a solenoid, that heater is gonna pop a disc up, which is gonna close switches. That gives you a little bit of time delay, which is why it's called a sequencer, because it brings your heat strips on in a sequence. So it's used to bring heat strips and fan on, uses a small heater and bimetal disc to close switches, no solenoid. So what is a bimetal disc? Many of the discs we use, or many of the components we use, have bimetals in them. That's just two different types of metal. Because metals expand and contract at different temperatures, if we put two metals together, and one of those metals expands faster than the other, we get a slight snapping motion. And you can feel it when you push down on it. Anybody want to push down on it to feel the snapping motion? We got hand wipes to wipe your hands clean here if you want to.
So you said you use two types of metals?
Yeah, we use bimetals in several different controls, not so much anymore because of technology, we have solid state devices, but a lot of times we use a bimetal. Again, it's two different metals put together, and so they'll basically just warp. When one metal heats up, it's gonna try to expand, but the other one hasn't expanded yet, so you're gonna get some type of warping or bending motion out of it.
So when it's energized, they basically.
Yeah, what's gonna happen on these when they're energized, our little miniature heaters inside of here are gonna get hot. I think this is the actual heater right here. So you see this little piece of ceramic material, whatever that is, that's what's gonna get hot. It's gonna sit, look inside here. So if I put 24 volts between here and here on the bottom of this solenoid, all this thing is doing is sitting there. As that voltage flows, it's gonna flow through this whole component and it's gonna get warm, just like a hot plate does. As it gets warm, it has discs sitting inside of it. Disc right there.
So you're just expanding the metal.
All you're doing is expanding the metal, and as it gets hot, it's gonna pop. See how that pops?
So is it creating a short to actually warm it up?
This is a resistor, just like a little heater. Just like you have an electric oven or something. It's gonna flow through that little heater and get warm. You have to go first, and move the hole in it for a second. And I don't have them, there they are. You can see these little poles. Those sit down in there and they connect inside of this. I don't know if these are made to go together. But basically when that metal bends inside there, it's gonna push up a plunger which will close between here and here. So your top terminals will close first. This will close to that and complete a circuit. After a short time delay, your second stage, that will close to that.
As the metal expands
As
more.
the metal expands, that's why you see we have two snap discs inside of here. One has a hole in it and the other doesn't.
Okay.
So one will snap first, then the other will snap to close the second set of contacts. Now, what's funny about it is we're gonna time it out there. This is supposed to close first. When this closes, notice this only has one set of terminals on each side. But this one has a couple of sets on each side. The reason for that is, we can bring power on here, and when this first one closes, we can send power to our heater and also to our fan motor. We never want a heater running without a fan to cool it off, or it's gonna overheat. So by having these two terminals, we can make sure we energize both our fan and our heater at the same time. Yes.
Would there be some kind of safety if the
Yes.
heater kicks on and the fan didn't kick on?
Yes, we have a couple of safeties in there. We have what's called a high limit switch in there.
Okay.
And the thing is, it's a bimetal disc as well. It's strapped right inside there where the heater is, and if it gets too hot, it'll pop. And it'll break the circuit, sending power to this relay. I said relay, I meant sequencer.
Yeah.
Yeah.
Another question, is it the same, does it have time lane as it comes down?
Yes, it has to cool off and then close.
Okay.
Yeah, or open, I'm sorry.
Open.
These are both, yeah, let me back up, both of these are normally open switches, so between, what's the label that, M1 and M2 is normally open switches. M3 and M4, normally open switches.
And when they're energized,
Yeah, our meter's not.
You already checked them to make sure they're open?
and when they're energized, they close.
Yep, between M1 and M2 will close, and then a few seconds later, M3 and M4 will close. What you'll learn when we get out here and we make these, some of yours will close at the same time. I've even seen some where the bottom closed before the top. And I've seen others where the top closes, and it's almost a full minute before the bottom will close. The same brand, the same manufacturer, bought at the same time. Just the way it is, so these are not absolutely flawless, perfect design.
And this is where your power comes in.
Yeah, and one of those, and it's really not uncommon to send power in here, and then jump it down around to there, so that you got power sitting on both of them. Just depends on how the manufacturer has it wired up.
Oh, power only goes into one side,
Right,
not, it leaves out.
exactly, yes,
Saves on wire.
right. So obviously down here is where I would connect my 24 volts. Once it has 24 volts, that heater's gonna start warming up. The first disc will snap, closing between here and here. Then after a small time delay, the second disc will snap and close here to here. Then as it's cut off and cools down, this one should snap open first. Then that one will snap open. First on, last off. Last on, first off. When I was in school, I asked my instructor, how do you check one of those? He said, when you go to take it off and it falls apart in your hands, it's bad.
So there's really no way to put a meter on it.
You can though, no, that's the thing, you can absolutely put a meter on this stuff and check it. But in real life, what you'll see happens a lot of times, if I'm gonna check this thing to ohm it out to see if it's closing, first thing I gotta do is what?
Take that.
Pull my wires off. Well, what happens when these things are bad, they get so fragile and brittle inside, when I go to pull wires off, this happens, the whole thing breaks and falls apart.
Okay.
So that was kind of his joke, was when they're brittle and bad, they normally all fall apart. But that's not necessarily true. You could have one stuck closed all the time when it should be, and there's lots of different ways of checking switches in that situation. You could kill power, take it off and home it, or you could just check your voltages across it, and see what you got.
If your power bill puts you in the poorhouse, it's stuck closed.
Probably is, yes. You're running all the time, heating your house with electric heat,
And the reason why it has a delay on the first set and second set is, putting certain amount
Right.
of power there.
Yeah, we're just bringing this heat strip on first, then after a small delay, we're bringing our second heat strips on. They make these in single stacks. This is a double stack. They also make them, let me see if I have one. This is like a double Big Mac with cheese right here. So you could handle multiple heat strips with this. It's basically two double stacks put together. You can see they brazed in a solid rod, so if I put common here, I've got common there. Same on the back side, if I put 24 volts here, because I'm a brazed conductor, I've got 24 volts here. So anytime I bring one on, I'm bringing them both on.
Did you have that out the machine? Did
Do
you
what?
that from the factory?
Yeah,
So,
janky,
yeah, that's a good word for it.
but you can control a lot with one of these, several banks.
Will these also be in like a water heaters?
Probably not a sequencer and a water heater. They use just a straight up thermostat, a high voltage thermostat.
Are
Just
these
curiosity.
Are these using those, the smart thermostats?
No. No, anything smart, a lot of this stuff you may not even hardly see anymore on new equipment. For instance, out there, there's 3 different ways we're gonna bring on heat strips. We've got sequencers on some equipment. We actually use contactors on other equipment. And then we have a DC relay, which some people call a DC sequencer, it's really just a relay, on others. So there's more than one way to do it, but you're gonna run into all of these. Questions about a sequencer? Ultimately, it's gonna wire up just like a relay. We put 24 volts down on the bottom. It's just instead of a coil, we got that little heater and a disc that closes switches.
Will these also be replaced by microprocessors? Eventually.
Well, that's sort of what we do with our DC relays. The problem with a microprocessor is it has to be able to handle 40 amps or something. And most of our micro stuff don't handle huge amperages like that. They can be used to control, like for instance, our DC relays is going through a board and then sent out to it. But the actual switches have to be able to handle the higher end.
Makes sense.
So you could very well use a board to stage your time. You send it out to the first relay and then 10 seconds later send it out to the second one, or however you needed to.
The thing is, these things are gonna be pulling about the same amp draw as your average garage. Like, so,
More than a garage.
I mean, well, yeah, more than a garage, but these aren't simple switches.
Yeah,
In terms
each
of-
5 kW is pulling 20 amps at 240 volts. Most systems have a minimum of 10 kW. So when you're running heat strips, you're pulling 40 amps just on those heat strips. If you have 15 kW, now you're pulling 60 amps just on your heat strips. Not to mention the other 20 to 30 amps in your compressor.
That's a third of your house speed.
And
right
your
there.
entire house is only supplied with 200 amps altogether. So this is a huge load
Yes.
electrically.
Oh, yes. Why do you get that big wire out
That's right. A lot of people say, how do you know if your heat strips are on? If you're at the equipment, amp it out. If you're seeing 20 amps on each wire for each set of heat strip banks, you know it's on. A lot of other guys will say, just walk over to the power meter. If it's spinning like a top, you're running heat strips, right? So that's what's gonna happen. It's not uncommon. If you have all electric heat, you could have $700 power bill easy. If you're just heat strips. Right now, these past few days, our heat pumps really struggle to keep up, and we're bringing on electric auxiliary heat a lot. So you're gonna see a bigger power bill. It's not necessarily Alabama Power just gouging you because it's cold outside and they know you need it. It's because our heat pumps are now having to run all this expensive electric heat. Questions so far?
I got one, but I actually.
Alright. Fair enough, let me put my relays back up. So when we go back out there to the lab, probably not today, when we go out there to the lab, we're gonna work on our lab projects. We're gonna turn this into a single pole, double throw relay and do that lab project. Then we've got a sequencer project and we have a double pole, double throw project. I wanna add to it that little scenario I was talking about before with this project. Does everybody have one of these? Devin, I'll give you one. Did everybody get this and the other picture we had yesterday? I'm gonna add this to it for our third project. All this is using a double pole, double throw relay in series with a sequencer to make sure I bring my fan on anytime my heat strips come off.
I didn't get
We're gonna do this on our board.
Do I?
We'll do
Yeah,
this.
we'll build all this on our board. So questions about sequencers? Are we good on them? Questions about single pole, double throw relay? Double pole, double throw relays? Anything we talked about, you have questions on? Good, I thought we were done. That's what we're gonna be using, but there is one more thing I wanna show you. We don't have assignments with these, but you will run into these occasionally in the field, depending on what part of the industry you go into. Residential, you don't see these a lot. You will on some old stuff. But if you go into commercial work, you're a lot more likely to see these. These are called, you can tell me, Ice Cube relays, not because they're rappers from NWA. You guys don't even know who Ice Cube is.
They local,
Do what?
anybody wants to see anything, listen to the show.
Skinny jeans.
Getting these in with.
I think new ice machines come with wrapping around them.
Do what?
I think new ice machines come with wrapping around them, that's what it means, right?
Yeah, yes, Ice Cube relay. Alright, let's look at this real quick before we go. This one's hard to see because it's printed on glass. Makes it really fun to read on. The light's off. A little bit. Alright, do me a favor. Somebody draw this on the board for me. Somebody with better drawing.
Logan.
Horrible.
Who can draw good? How about you, Peter? Peter? Come on, Peter. You were drawing on the board, Peter. What am I drawing this thing? Alright, I'm gonna give it to you. I just want you to draw a big version of this on the board. Sure about that, Peter? check this. Should be a mirror image of that side. Looks right. Thank you, Peter.
Rectifier diode?
Mm-hmm. It is a diode. Cool thing about a relay, an ice cube relay, is that once you have it wired in, if it goes bad in here, you unplug it, plug a new one in. You don't have to rewire. That is nice. When you have, how many terminals on this thing? 1, 2, 3, 4, 5, 6, 7, 8 terminals hooked up to this thing, all screwed down. If it goes bad, you really don't wanna have to trace all that stuff out anyway. You don't have to. If it's bad, you just pull it off. That's all your mechanics. Chuck it, get the replacement, plug it back in. Yes.
Unless you see a burnt wire on.
Yeah, unless you got some burnt stuff inside these terminals here, then you're in trouble.
Yeah.
But hey, we know how relay works, so we can fix those, can't we? All right.
That's different from the 6 I was looking at on the 6. On the doors on the board. Oh,
It's pretty much the same, yeah.
okay.
Yeah, they're doing the same thing. Does this make any sense to you guys? Oh, I forgot my lightning bolt. Gotta have that lightning bolt right there. All right, man in the back left, yes, sir.
Why is there a rectifier on it?
Rectifier, what is that a symbol for, guys?
No,
Diode, right?
That's
which
just
is a
like-
rectifier. If I look at this thing up close, do I see anything on there? When have I ever heard the term diode?
Oh, it's an LED, okay.
What about a light emitting diode, an LED, an LED TV, all this different stuff, any kind of light? Diode that releases light is a light emitting diode. All they've done is, this is basically my coil voltage right there. So between 7 and 8 is my coil voltage. Why do you think they wired up a light in in parallel with that coil voltage?
So you can tell when it's on.
That's right. So with this type of relay, anytime I have power between 7 and 8, I also have power on that light. That light will glow red to symbolize that relay is energized. Does that make sense? That's all that goofy picture means. If I'm putting power on my coil, I'm also putting it on this diode. That's D-I-O-D-E. Which gives off light. This little indicator light. So, what am I normally closed between 6 and which terminal?
2.
Normally closed
Oh,
between
no,
6
closed.
and 2.
Sorry.
It's not hard to see now, is it? You guys are getting good at this.
That's it.
Yeah. Now then, Peter, I'm normally open between 6 and what? 4. All right. Stephen, I'm normally closed between 5 and what terminal? 1. Jesse, I'm normally open between 5 and what terminal? 3. Gavin, if I energize this coil, will I be open or closed between 6 and 4? So with this coil energized, will I be open or closed between terminal 6 and terminal 4? Yes, if I energize that coil, that means I'm gonna close 6 to 4. All right, Jesse, if I energize this coil, will I be open or closed to 5 and 1?
Open.
Open. You're getting the hang of this? Understanding how it works is obviously the first step, right? But the second step is knowing how to check this stuff. One way is to disconnect all power to everything and home out switches. That's a lot of work, right? The other way is to check voltage. But checking voltage can be tricky because you can back read voltage from loads that are connected to it. So we need to become really good at knowing how to check voltage to see if a switch is open or closed. But we can get to that a little later on. Does the ice cube relay make sense? The last thing about them I want to show you is how to find 1, 2, 3, 4, and 5. That's not there just for my demonstration purposes. All of these should be labeled. If I can see them, I don't know. Kind of starting to come in. Can y'all see them now? So as long as there's labeled, and as long as I have a little schematic, I can figure out anything I want to about this relay, can't I?
And your reading glasses.
That's a reading light. You might want to keep a magnifier with you, some of this stuff's hard to see. But that terminal is 1, that screw terminal is 2, 3, 4. Looking at them here, just like some of our contactors and different things, you just screw it down to tighten that wire inside of it. See if we can focus in on the back side. My top 2 or which ones?
5 and 6.
There we go. 5 and 6. My bottom are
7 and
7 and 8. Looking at my picture, which one are my 4? Which one should I put my 24 volts on?
7,
7 and 8, right? Which was, I said these two little ones right there. Assuming this is a 24 volt coil. These coils could be 120 or 240.
Why is it called an ice cube?
Cause it looks like.
It looks like an ice cube.
So it's just a nickname.
Yeah. So it does say that this is 24 volts AC. And you can see my coil is actually wrapped in paper, plastic. It says 24 volt AC. And again, if you wanted to look at this, you can see all the little connections being made or broken inside of there. Actually, flip. How do we feel about relays now? Strong? Good. It's Thursday. We'll be back on Monday and we'll be in the lab all day building little projects and doing some tests and stuff. You put your time in the trenches in here, so.